past 5 and it's too late. Okay, so recall what we did last time, which was we were introducing thermodynamic functions that are actually these, I guess I'd use the word predate. Delta G and delta H, you had delta G and delta H as freshmen, and maybe you saw in some other classes. This is actually the innards of delta H and delta G, which is delta U, or just U, right? We talked a little bit about deltas versus exact and inexact differentials and all that. Anyway, all right, remember there's the equal partition theorem that says if you can count out the degrees of freedom, you can figure out what the internal energy is. The internal energy is the energy a molecule has. And again, if that sounds like I still don't quite get that, that's okay. If you don't quite get it, you will once we introduce other thermodynamic functions. Okay, whatever. The energy a molecule has, there's some 0 degree energy, but we're not going to worry about that because it doesn't move our car anywhere. And then we've got this degree of freedom times 1/2 RT thing. That's the equal partition theorem. We covered it. And this is what it is. Now remember, it's a helium, neon, yada, yada, yada. Those are easy. They can bounce off walls in 3 directions, and so 1/2 RT times 3, there you go. Now remember, it gets funky when you get to diatomics, which is basically everything, because vibrations don't count, and I'm going to re-emphasize that again, so I won't bring it up now. But vibrations don't count, and so what you have are 3 translations plus, another little funkiness with linear rotors. CO2 does not rotate like this. I can't rotate helium, that's why it only translates. CO2 rotates like this, it rotates like this, but it does not do this. That doesn't work. So there's 2 rotations, 3 translations, 5 degrees of freedom. That's why it's not 9/2, but 5/2. Okay, being nonlinear, methane actually does rotate in three ways. Again, that's because we live in a 3-dimensional universe. Just the same as there's 3 translations, there's 3 rotations. Why? 3 dimensions in our universe, and everything else is a vibration, but vibrations don't count. There you go. This is going to come up a lot and probably will be on the test in some form or another, by the way. Okay, now we also then talked about work, and I tried to justify the fact that there is a minus sign by talking about dot products and relating work to force times distance, but we're going to do gases, so it's really going to be pressure times change in volume. I showed you how pressure times change in volume is really the same thing as force times distance. There's a little funky dot product. You also got to consider whether you expand or contract, and that just naturally leads us to a negative sign. Now some of you are a little bit worried about, but I need to know which direction it goes in. No. The minus sign takes care of that. Forget that direction stuff. I just wanted you to be okay with the minus sign. The minus sign takes care of that little dot product no matter what. The point is minus. Okay, so that was work. And we should put a little star by here. Okay, now we had already covered that work is path dependent. The differential is inexact, so it's path dependent, and we discovered that there were 2 paths. One was the irreversible, in which case that was I kind of screwed up the example. Whether it's easy to understand compressions or expansions depending on the problem. Magic cylinder, right? Big magic cylinder, and actually an expansion is the easier one. So I'm pushing with the force that a person can push, which is about 2 atmospheres. And that's about what a person my age could push. And I suddenly let go, and of course it expands, and of course it'll expand until the interior pressure is 1 atmosphere because the exterior pressure is 1 atmosphere. I'm going to put that in question to hear what I just said. Why would the piston, when I let go, stop expanding? Because the interior pressure is the exterior pressure. That is part of the problems I will ask, but I'm not going to tell you that. You should just know that. Okay. So so to get the fine idea, remember these are 0, probably on the test. They need to be integrated for them to have meaning, so I integrate it. Now I can take the exterior pressure outside of the integral, and because it's constant, that's the definition of irreversible as we know it right now, and here you go. There's our formula for work, and that's the irreversible path dependent. Now there was also the reversible path, And remember, that was to calculate the work. Of course, I need to integrate. I need to integrate the partial, otherwise I don't have meaning. And again, expansions are easier to understand, so I'm pushing with my 2 atmospheres. And I slowly back off. Slowly, I always just introduce a very slight differential from the interior 2 atmospheres until I finally backed off and let go at 1 atmosphere. Now the point of that is that the exterior pressure is a function of the interior pressure. They're basically the same. So I'm not going to write external pressure, I'm going to write P, and that means internal pressure. Again, a little shorthand, you need to be aware of that. Now, one rule of integrals are pressure is hiding the letter V. I must draw it out. Or, if I don't, the integral will change. The integral of dx is x, but the integral of 1 over x dx is ln x. It matters. Now here's the thing. Here, pressure didn't hide the volume. It wasn't a function of it. This time it is. So again, I draw it out. Okay, so I'm going to use the perfect gas law. I'm not going to do any trickery with van der Waals equation. That's just too painful. So don't stop thanking me. nRT over V dV. And you can see why I gave you that example. Oh, and I need limits. Sorry, V, I, VF. Now sometimes I screw that up and I'll write V1 and V2. I'm not trying to, that's not different. I'm not trying to be difficult. It's just I make that mistake. 1 and 2 versus I and F, initial, final. Got crunched up there. Anyway, yeah, there you go. Now, of course, remember that these 2 paths are really just represent, these are the extrema in how engines actually work. Engines are more irreversible than reversible. A reversible engine is perfect, no friction. You're going to see a little bit more what it means to be reversible. That's a little bit more technical. In about a month, we'll go over a little bit more about what this means. But no engine is perfect. Engines are pretty far from perfect. And so most engines are more irreversible in nature, but maybe not fully. As engines become more efficient, they pick up more reversible character. In other words, this is black and white, but the world is a shade of gray. That's the take-home lesson. We're not going to cover shades of gray because that's too hard. This or this, it'll be absolute. And let's see, that's all, yeah, that's actually all I had to cover on this stuff here. And then we did some graphs, but I'll skip that because that was on your homework that you just turned in, so I think you're okay with that. I'm going to show those graphs again of P versus V to explain work. So this was work. And remember, don't write this down, but remember that I was explaining work because I was talking about internal energy, and that was work plus heat. Now don't write this down. I've explained work. That's actually really all I've got to say about work, so let's do heat. Heat is a funny creature. Probably, actually, I should explain. Remember, there's no heat, there's only changes of heat, so I shouldn't ever say heat, but I'm going to anyway. There's only changes of heat. There's only heat transactions. There's no actual Q, there's only a change in Q. Remember, it's an exact. You're actually going to prove math, you're going to do a derivation to show that heat is an exact later. Just don't worry about it now. Okay, what do I want to say? Okay, so I don't really have much equations for heat. Work, I got the magic piston. I've got ways I can expand or contract it. They lead to different equations. I've just done that. It's really not that hard. Heat is a little different. Heat is I've got the magic cylinder and I've stoked a fire underneath it. That's all I've got, really. When I ask a heat transaction, largely I'm going to say I've added 100 joules of energy in the form of heat to the magic cylinder. That's it. And so you just write that down and you got a point. I can't really do more than that. I kind of have to give it to you when I'm talking about something changing by a heat transaction. It's actually rather boring. Maybe I should have started with heat. Regardless, there is just one bit you do need to know, and what's positive, what's negative. Remember, I was telling you. All right, some little rules. There's only positive pressures. There's only positive volumes. They're not negative. And it matters whether something is positive or negative. That's heat in, heat out. And work is expansion. Remember, that would be a negative work, and compression is a positive work. And so at that, you really want to know that. Doesn't get a little star, all right, but it's kind of important. So now let's do heat. Now, if I'm going to stoke a fire under the magic cylinder, and now I've got to tell you it's 100 joules, but now you should say, is it plus or minus? Right. Now I said plus, I said 100 joules, that means plus. And so therefore, a heat transaction that's positive is storing energy. And maybe in your little side notes say I put a fire under the cylinder. Right? That's heat going into the system. Right? So that's kind of what your natural inclination is when I talk about heat. You don't think of things shedding heat, you think of adding heat because you are the actor generally in everything that you do. Okay, so therefore negative is, how do I put this? It's shedding. Shedding energy. Excuse my poor grammar. Okay, heat in, heat out. You want to keep this straight. Now here's how I'm going to ask this on homework and on tests and when I'm talking. Okay, you're doing a question, and I'm going to show you, there are a couple of equations for heat, and I'm going to cover them in a minute, but whatever. The magic cylinder did something, and the heat was positive. The heat was positive, and now you touch it. Is it hot or cold? Reasonable question. Now tell me. You just know it's storing energy. Is it hot or cold? Cold. It's cold. I was right. It's cold. Heat is going into it. What's the heat source? Yes, you. You are the energy source. If you're losing energy, you're getting cold, ergo you feel cold. You don't feel it. It doesn't feel anything. It's heartless, like my last group. Anyway, so it's taking your energy, you feel cold, but you put energy into it. And remember, we think of things from the system standpoint. I don't care what you feel, because heartless, but I really only care about the magic cylinder, because the magic cylinder drives the car or keeps the lights on. Now, you do gas expands, a gas contracts, yada, yada, yada. Oh, I got a delta Q, and I ask you, well, is the magic cylinder hot or cold? It is correspondingly hot. The other one was, look, or up or down, all right? Yeah, one's hot, the other is cold. So shedding energy means the heat's coming off, you're absorbing it, therefore you're hot. Okay. Now I have a little mnemonic. Now remember also, again, signs are really important, right? Because energy in is very different than energy out. So signs are very important. I don't want you to memorize this. I have a little mnemonic for you that'll help keep things straight, but you don't need to memorize what I'm about to tell you. It is helpful to keep this plus minus stuff straight in case you've done the question wrong. Let me write down the mnemonic first. And I call this the energy bank. Energy bank. And this is simple. It's positive to store energy. Which you know that's true. We're running out of oil. Actually, I always take half a lecture to explain to you what's going to happen when the world runs out of oil. That's a little over 30 years from now, we're going to start running out of oil. Yeah, I'm going to scare you really badly. I'm glad I'm going to be dead. I'm not kidding. Anyway, that is kind of funny. Okay, so the energy bank, of course, is positive to store energy. All right, positive to put energy into the cylinder, and you do that by lighting a fire underneath it. Fine and good. For compression's positive, right? The reason, the thinking there is that when I'm pushing the magic plunger and the magic cylinder, what I'm doing is I'm spring loading it. I'm giving it the capacity to do more work later, which is energy storage. Therefore, it's positive. Now, why am I telling you that? If you do the equations right, you don't need to remember that at all. You will naturally get it right. You don't need this to answer the question correctly. You do need this. This you need to know. There's a star by it, and it's on the cheat sheet. However, you're at the test, you're nervous, and you would like to know very quickly whether you got it right or wrong. Do this. Did you get the sign right? See, if you got it wrong, if you answered the question wrong, it's 50-50 that you got the sign wrong too. If you've done that now, you know. If it's compression and you got a negative work, you've done it wrong. Do it over again, right? Or come back, wait, just put it aside, you got it wrong, put it away, so that you clear your mind, you hit the reset button, then go back and do it again. That's why this might be helpful. But don't try to memorize it, your head's full of stuff, because You don't need it. You don't need it. Anyway. Okay, so I do have some equations for heat, and these are really kind of trivial, so I kind of hesitate to say that. So let me write this down, equations. So I do and I don't. Sorry, I'm OCD, so that bothers me. The key wasn't perfect. So I do not have an equation for changes of heat like LMV, F over VI, and I don't have that. But I do have this. And of course I have to introduce paths because this is path dependent. Let's say that we're doing things isothermal. So the magic cylinder expands or contracts and it's isothermal. Okay. Now again, you're at the test, you're looking at number 5, and number 5 starts out with the magic cylinder. It expands under isothermal conditions, and it has a mole, and it was at 5 liters, and What's the work, heat, temperature, final pressure, final volume, change in U, and then I got a couple of others. Remember, there's 48 total. Yes, there are. Okay, so now, of course, the change in heat is one of them, so we got to get it. Okay, now it turns out that before I ask you the change in heat, again, the magic cylinder expands or compresses at constant temperature, which is isothermal. The first thing you want to ask is, what's the change in U? And what is that?
0.
Right. Now, okay, the answer is 0 joules, by the way, that you just lost a point. It's 0 joules because of the equipartition theorem up there. We covered this last time, just watch the video. The equipartition theorem says that the internal energy, give me the degrees of freedom, and of course you don't change those. It's because the cylinder expands or contracts. You don't change the degrees of freedom. That'd be weird. That's not happening. You do change the temperature. Oh wait, no you don't. If you change the temperature, you get a change in U, because that's the only thing that matters. But this is the temperature doesn't change. Okay, so there's no change in U. It's blindingly easy. Notice though that this is heat and work. Okay, so I kind of do have an equation for heat. It's minus that of the work. There you go. So it is. Now I've got to do my reversible, irreversible. You may notice that I've defined actually 3 paths, by the way. Let me just write this down. Reversible heat would be nRT ln dF over VI, and irreversible heat is just PEXT delta V. The minus signs are gone, okay? So again, now these are, remember I said 48 different equations. Here's 2 more. Or is it really? Do I have a star? Okay, you know what I mean? I do need a star by this. Okay. Now remember, I'm prepping you all the time because I want you to do well because it makes my life a lot easier and makes me look good. Okay, there's very few things I want you to remember. This is one that U is the change of heat and work. Again, it's on the cheat sheet. And isothermal, via the equipartition theorem, the change of U would be 0. Okay, you got that. And then drop it. Right? That's all you need. Therefore, you got this. Now, you don't need to memorize this. See, you just derived it in your head. You derived it. You remembered this part, but you derived that part. So you don't actually try to memorize it. Now, you've also memorized the formula minus exterior work EV, which gave you these guys. You just slapped on a minus sign, and there you go. You got all this stuff, and you didn't memorize anything. So that 48 is now actually what? 5, 1, 2, 3, 4 things. We just whittled off the 48 conditions. And anyway, so we're going to continuously do that as we go along. And there you go. Last bit I said was that notice that I'm defining a couple of paths now. Now I've already defined reversible and irreversible path, but notice that those can happen under isothermal conditions. Okay, so that sounds like three things I got going. I got reversible, irreversible under isothermal conditions. Sounds like that's a mix of 3 things I could do, and that's of course true because there's another way of the magic cylinder expanding or compressing, which let's call it not isothermal. I'm going to give this another name in a little bit, actually next lecture or 2 lectures from now. Right now, let's just recognize that there is a way to make a gas to expand or contract where we don't keep the temperature constant. What would I do to make it, okay, magic cylinder, it expands if it's at 2 atmospheres. I'm always doing like, it expands at 2 atmospheres to 1 atmosphere. Okay, the magic cylinder's at 1 atmosphere, how else can I get it to expand? And we're talking about heat. Seriously, what do? You heat it, right, fire underneath. What happens to the temperature inside of it? Goes up, right, of course then it expands. Oh, you can heat a gas. Yeah, you knew that. You didn't need this special class to know that you can heat a gas and make it expand. You can cool it and contract. It's a little easier to think of heating. Okay, so you knew that. All right, now I got to think about heat transactions when I'm not isothermal. And by the way, don't write this down. I just want to point out a little bit of what's happening here, but don't write this down because I'm going to come back to it later. Reality is when you're doing some tricks on the magic cylinder, let's do expansion. You know that you have a refrigerator, and you know that gases tend to cool when they expand. That's how your refrigerator works. We're going to go into great detail on that later. That's why I don't want to talk about it now. All right, you know that the refrigerator needs to cool when it expands, but the condition was isothermal. What happened was heat went into it to prevent that from happening, and that's why the magic cylinder is made of metal. Again, the magic cylinder was at 2 atmospheres. I let go, and gases expanding generally get cold. And but I said it was isothermal just because I said it was. The cylinder is made of metal, so heat will go into it. And in fact, this much heat will go into it to basically negate the work, so that the temperature is the same. All right. So anyway, now what I can do is I can just straight up heat the thing. And I guess I'd have to thermally insulate it, but anyway. All right. Now, if I'm going to think about heating something up, and I'm not going to let the damn thing cool off like I did before. I need to start figuring out how to do the energy. And I normally would ask you folks if you know this, but let me just tell you what you need to do is use heat capacity. And this is when you started learning about a calorie, which is 4.184 joules, right? Which is the energy it takes to heat water up by 1 degree, right. So we're back to that stuff, but we're going to do it with the gas. Actually, this is going to be slightly easier than heating water in the base. Okay, so I need to define heat capacity, and I'm going to use the letter C. And I'm going to think about, again, the finite amount of fuel that I have to burn to generate that energy. And remember those Hess's Law type questions of methane plus oxygen goes to CO2 plus H2O. Remember those? We're going to do it in class. Okay, so the heat capacity is the amount of heat I add to something, and what I've got is, of course, a change in temperature. Again, this is not the metal magic cylinder. This is a magic cylinder which took some heat, and then I wrapped it up in glass wool or something like that to keep it insulated so it stayed warm. All right, it's a little different than here. Okay, so that's the definition of heat capacity, except that, actually, I stupidly did not leave myself room. Here's a little, this is not important, by the way. You can actually leave what you wrote. Actually, I have to define this as a limit, and I'm just being overly careful because, as I said many times, I do not believe in simplifying things to the point that they're not true. Technically, I need to do a limit of the temperature going to infinity, infinitely small, sorry. And now you know that I can use the language of calculus, the language of partials. And I have to do that because, so why? Why am I doing this? Because C is temperature dependent. And I'll write that out. It is T dependent. Here, I'll raise the board here. Okay, so again, if C is temperature dependent, you can't just define it like this because the amount, because this is a single number, but there isn't a single number over a range of temperatures. You see what I mean? I can't think of the heat capacity if I'm measuring it from 0 to 100 if the heat capacity changes from 0 to 100. That's a flawed measurement. There's no answer to that. or there is, which is that you define it at a particular temperature, but that means your measurement is over a vastly small temperature range. You actually do this with Heat Lab, by the way. So when you do heat capacity measurements, you often measure like 0.01 temperature units, little tiny jumps, and of course that also means we like to use the language of calculus. So, what else do I want to say about that? This is kind of a pain, but there's not really much I can do about it. And let's see, what else do I want to say? Oh, okay, so there's another thing about this, about heat capacity. So again, it's temperature dependent is one. The other is that it is path dependent. And you should be able to guess that because it's equal to the change in heat, which is path dependent. Now, I'm kind of hoping some of you are thinking like, okay, heat's path dependent because it's an inexact differential. You're actually going to formally prove it in a homework question, actually in class and on a homework question. And so definitely I'm thinking heat capacity is going to change depending on how the change goes about. I will explain in a minute. But I'm also wondering if dividing it by the change in temperature maybe negates it. Kind of like extensive over extensive equals intensive. No, it doesn't. And again, I'll explain that in a little bit later. But path dependent over, I don't think that's, I don't even know whether I call it change in temperature path dependent or not, but anyway, path dependent. Okay, so depend on temperature and this path dependent, there you go. All right, now, let me introduce the paths, and then I'll give you some numbers. I do want you to get out of here. One of the things I want you to get out of here is, there's certainly going to be some details. Like I just mentioned one, that it takes 4.184 joules of energy to heat a gram of water. Yeah, it's a gram of water, is that right? Right, 1 gram of water, 1 degree Celsius, isn't that right? So little factoids. Now I remember that because I'm a freaking professor and I never left school. But when you graduate, you probably won't remember. And you know, I don't think your life will change at all. It'd be pretty weird if you were in some kind of SAW type of situation where you had to remember that the heat capacity of, no, it's not going to happen. But I would like you to get a sense of scale for energy, how much energy we have in oil, right? Because it's not nearly as much as you think. It just seems like it's infinite because the lights are always on. 35 years, those lights will be on about 2 hours a day. That's all we're going to be able to afford. I'll explain that in a little bit. And there's no avoiding this. The only light you're going to have on all day is that, the big one up there. And that's going to be hard to see because we're going to burn coal, and the sky's going to turn black. So actually, that one's going to be snuffed too. So the matrix is actually a document. Anyway, so let me go on. Okay, let's talk about the paths. Okay, so I can basically take the magic cylinder and just stick the plunger, stick it in place and heat it up. Obscenely dangerous. In chemistry, we never try to do reactions adding heat to a closed vessel. It's easy to do, but you'll kill yourself. Regardless, it's something that can be done. It's a path. Constant volume is kind of like a path. So if that's the case, what's nice about this is, again, it's very sensible. How much temperature does the gas in the magic cylinder go up if I heat it? Oh, by the way, the plunger's stuck, right? So you can see all those qualifiers. That's path dependence for you. All those qualifiers. I need them to define the path. Okay, so at constant volume, let me do this. All right, for one, we're going to need to determine what the heat capacity, but I'm going to use a little d to show that it's constant volume. Okay, let's do the change in U, which is the change in heat, and this will give me the heat capacity, but the problem is I also have a change in work. Okay, now this class, remember, work is going to be PV work. In other words, the gas expands, the gas contracts. We're at constant volume, and the answer to one of your homework questions is, I can get rid of something, which is it? It's work, right, there's no work. At constant volume, there's no work. It was on your homework. Right, no volume change. Now, in case you thought, oh, well, no, it was this. No, that's isothermal. I didn't say it was isothermal. In fact, I said it was the exact opposite. This is the non-isothermal case. It has a name. I'll give it in a week. Anyway, Now, CV is the change in heat over the change in temperature, which is now the change in U over the change in temperature. So what? It'll matter in a little bit. Now, also recall that in the language of multivariable calculus, I need to specify what's held constant with this little odd symbology, and there you go. That's the heat capacity of constant volume. What's good about this is that, now remember I was saying that I really don't have great formulas for heat. I just have to tell you what it is. Or if it's isothermal, I can hijack Work's equations. But I don't really have an equation just for heat on its own. But I do for U. I got lots of equations for U and changes of U. So that's useful. And especially in a minute, you'll see what I mean. Let me also show you again the scale of things. And so I'm going to, I told you before that I need to PowerPoint sometimes, but I don't want to, so I don't. That's because I feel empowered to do what I want. So I'm going to draw heat capacity as a function of temperature. We will go from 0 to 0. And here, sorry, let me give myself some room to write some numbers. And notice that heat capacity has units of R, so that allows me just to write numbers. And so I'm going to write the number 5 halves. Now all things have units. I divided out the units, which you're now comfortable with. So 5 halves, and I will go to 3. And because this is, what am I doing? This will be for N2, O2, and other diatomics. N2, O2, good enough. Okay, so here's what happens. In the tens of kelvins, remember never use Celsius. I'm always shocked to see people use Celsius even at this stage of the game. Okay, in the tens of kelvins, what's happening is that the heat capacity, I believe it's technically 0. Actually, I'm not sure about that. Sorry, I may have screwed up. So what's happening at these low temperatures, and let's say that this is already, well, things are frozen, they're solids and liquids, but what's happening is they're starting to translate. And so that means that we're thawing translations. So what's happening is that this notion of degrees of freedom that define U, which define heat capacity, they're temperature dependent. So, sorry, I guess I didn't plan well for what I wanted to say here. Okay, let me back up. Okay, U is defined by degrees of freedom. Changes of internal energy are used to define heat capacity. I'm drawing heat capacity. I need to think about degrees of freedom because there it is. Okay, when something's frozen, when I warm it up, what's happening is it's just kind of starting to translate. Now, if it's in a solid or a liquid environment, it doesn't translate far. When it's a gas, it does, whatever. Same idea. It's translating, and as it translates, as you heat it up, it can translate more. And that's like saying you have more degrees of freedom. It can do more because you gave it the energy to do so. And so the heat capacity rises. Then you get to the terrestrial temperature, where things, of course, everything always translates. But now you're translating and rotating, right? Because now you're a gas and you can rotate. And this is where, see, heat capacity tends to level off. Now, because I'm doing N2 and O2, which are linear rotors, and we just went over this, the heat capacity is 5 halves. It translates 3 ways and rotates 2 ways, 5 halves. At terrestrial temperatures, so sorry, I'll just call this room temp. At room temperature, all those degrees of freedom, again, translational, rotational, those are unthawed. Those are the language, that's the language we use. The degrees of freedom are unthawed, and now it has enough energy to translate and rotate. Now that also means that we're not unlocking more degrees of freedom, again, at terrestrial temperatures, so the heat capacity kind of levels off. It's still rising, but not by much. And so when we do heat capacity questions, I will give you the heat capacity, and you can just forget the fact that it actually changes with temperature. It does, but it's slight. I'm going to ignore it, except for maybe once or twice. Okay, now you know that when you get to the rocket engine, I know this isn't really to scale, when you start putting gas in a rocket engine or inside the sun, you're gonna vibrate, you're gonna translate, and you're gonna rotate. Now remember that so it's probably easier to see maybe why it rises. This, when you're unthawing something, that actually really is kind of complicated. And we'll actually cover a little bit more about melting solids and quantum, so let's not worry about this. But from here to here, I hope that this kind of is clear why heat capacity is rising. Remember that in, how do I want to put this? Remember that rotations, for something to rotate with a higher quantum energy, it rotates a little faster. And if I go to another quantum state, it rotates a little faster. And if I go to a higher quantum state, it rotates a little faster. But you can barely tell that I'm doing anything, right? Hopefully. Vibrations, when you're at the ground quantum state, you have X amount of energy. But for you to absorb more energy to the next quantum state, you're doing this. There's no in between. So this is why at room temperature, you don't absorb energy into vibrations because there's just not enough energy. So you just don't worry about them. They don't exist, right? And this is why the heat capacity ignores those vibrations. This is why it is not 3, it's 5/2. Wait, so 6? Yeah, I did that right. Now, as you warm up, RT is equal to that vibrational energy, and now the molecule can suck that thermal energy and vibrate more, and that means it has a higher heat capacity because it has more degrees of freedom. So anyway, if that's a little unclear, maybe you want to watch this a couple of times, and that might help. Let me actually, here's another way to do this in case it's not clear. Let me define U, in case this isn't clear. This is just another way to do it. U is 1/2 RT times degree of freedom. That's my shorthand. And I just said heat capacity at constant volume is the change in U with respect to T, which is 1/2 R. T is gone. See, this is the degree of freedom. Degrees of freedom. So at room temperature, plus and minus a couple hundred degrees, well, I guess not minus, but anyway, at room temperature, you've got 3 translations and 2 rotations for 5. Therefore, the heat capacity is about 5/2 R. I divided by R, 5/2, there you go. It's perfect. It's exactly correct. On your next homework, you will actually look at data, and you will prove this relationship is true from the data. So anyway, yeah, that's really all I have to say about this constant volume one. Now let's do constant pressure. I see that you're chomping at the bit to get out. Oh, wait. Okay, I've got about 3 minutes left, and then we're going to get out and get your homework. Let me do, I did constant volume. Now, who can guess what the next one is? Constant pressure, right. Okay, now that is the magic cylinder with the plunger unstuck, or better yet, what I'll do is a balloon. So this is me heating a balloon. All right, so this is the other path that we can follow, the other way of doing things. And I need to spell it out, constant. Come on, folks. We're not New Zealand, right? We have to do this, right? Anyway, okay, constant pressure. Now, in this case, what I'm going to talk about is CP, which is still temperature dependent. And again, I'm going to just drop the temperature dependence. I'm not going to make that a big thing. I want you to know, but not to worry about it. There's 2 things you need to know, and that is CP is greater than CV by this amount. Heat capacity at constant pressure is greater than the heat capacity at constant volume by this quantity here. I'll explain this. We're actually going to derive this next time, so I'm going to drop it for now. But one thing I do get out of this, you may not have noticed this, is that heat capacity has to be size dependent. For the difference to be dependent on size, that means that the heat capacity, constant pressure, or volume are also size dependent. Now let me explain this this way. Let me do this in a way that I just said kind of not to, but I'm going to do it anyway. Let's look at the finite change in heat of the heat capacity, and I'll just do constant pressure. And this is how you get the finite change in temperature. Again, ignoring the temperature dependence of heat capacity, which I said I'm going to do almost entirely. Okay, now, it takes a certain amount of energy to heat a cup of water at 1 degree. It's not a lot. Okay. Certain amount of heat, not a lot, probably a big lighter can do it in about a minute, and heat a cup of water by 1 degree. Now, 1 degree change for the ocean. Bigger? More heat, right? Okay, this went up. Now, my point is, temperature stayed the same. Well, that don't balance. Unless, what? Unless, this is bigger, smaller? Bigger number over smaller numbers even get a bigger number. Right, bigger. Right. If you're going to heat the ocean to the same degree as a cup of water, of course it takes more energy, but that just shows you your heat capacity is size dependent. Now, note that the units are joules per K, but you often see them in the form of joules per K per mole, which is R. That's just a shorthand. That's just a way to put this information in a data table, right? If I'm going to give you the heat capacity of water, I'm going to give you joules per K per mole. And then you multiply it by the number of moles, and now you know the true heat capacity. That is a trap that will get a lot of you on your questions. Whenever I give you a heat capacity, it will be per mole. You need to multiply it by moles. Every time I will do it to you, every time. I'm not going to give you 1 mole for anything. All right, so look out for that. Okay, so that's one factoid about heat capacity. That its size, it's actually extensive. Okay. What else do I want to say? Okay, so there's this. The last thing I want to cover actually is why is this true? Why is the heat capacity at constant volume greater than the heat capacity at constant constant pressure greater than heat capacity at constant volume? Now, if I heat a balloon, sorry. I'm going to heat a balloon, but I'm going to use the force. I'm not going to let it expand, and it's going to get hot. It'll get pretty hot pretty quick. Now, I release the force because I'm Kylo Ren, and that was cool with that bullet. But anyway, you know what I'm talking about. So I now release the balloon and it expands. Would the balloon be as hot? What did we just say about expanding gas? It would cool a bit. So in other words, so what if I just let it expand to begin with? So again, a balloon has been heated, but I'm not letting it expand by the force. And now it's hot. But now I release the force and it expands and it naturally cools. Now what if I just never added the force to begin with? It would expand, but it would not get as hot. Okay. So that means that the heat capacity at constant pressure is bigger. Now, I know what you're thinking, well that means it got hotter. Let's go back to this. For the same rise in okay, so sorry, let's do it this way. This is bigger. If this is the same, then your temperature is not as hot, right? They have to balance. The equation has to balance, that's how. So if you had the same amount of heat to something, and knowing that the heat capacity, is bigger, that means you're going to get less temperature range. Now here's why. The expansion of the balloon is what kind of work? Just, what kind of energy is it? Work. It's work. It's work. When you let the balloon expand, it's doing work, and so you lost some of that heat to work. If you lost heat, you don't get the same temperature change. You got me? Again, I added heat, but it did some work because it expanded. That's a change in volume. That's energy, and so the energy didn't heat it up, so it didn't get as hot. There you go. All right, so anyway, with that, that's all I've got.